Okay, whenever you are ready, Elga and Gary, you may start your presentation.
Okay, so good afternoon, Pak Dedi. Good afternoon, Bu Lydia.
Bentar
Today
ya,
we're
saya nggak kedengeran bentar saya ini.
okay.
We have
Yeah,
to
okay.
explain from the first one or just jump to the revised ones?
You go from the first
We
slide,
just do that.
although your pace may be a little bit faster, yeah, for
Okay.
the background, etc.
Okay. Good afternoon, Pak Dedi. Good afternoon, Bu Lydia. So today we're gonna present about what we had in this couple of weeks. This is about our mechanical support for spinal muscular atrophy or SMA patients. I'm working this project with my colleague, with my partner Elga. So first, the first slide. So what is this about the spinal muscular atrophy or SMA? This is a disorder. Is a neuromuscular disorder. So it's a combination. It's not limited to only muscular or not only the neural system. It's both between the connection of that system, and it's caused by specialized loss of specialized nerve cells. It complicates the muscle weakness condition. It usually complicates to that condition. So what are we going to build? Is to basically make a simple mechanical support for their arms, so they can move the designated part of the arm, so they can train the muscle to strengthen it, and also to prevent extra movement of the arm, so then it won't broke the joint of the patient, and also the daily activity support. Next. So what are our targets? The first one, create 1 degree of freedom of the arm, that are abduction and adduction, and then to smoothen the movement of mechanical system, and then detect neural activities, and then and then actuate the muscle activities. So for the principle of design, we already changed it. First, we made it on the two-dimension design, and then me and Elga tried to build it in 3 dimension, though it's not that good. I tried to make it on Tinkercad, uh, and I tried to apply it on the same amount of uh, size, and these are the result. So the first we uh, we applied the same length and width of the arm and the body, uh, all of the body measurement that has been given by Sam Andrew before. And then we also put the wheelchair length, though the width is unknown, so we just put it a approximation there. And then we put the pulley right here. This is also I use the scale of 1 millimeter, one 1 millimeter and 1 centimeter here, so 1 per 1. uh, so this is 5 millimeter here. In real life it's 5 centimeter, and then we use two pulley with the same radius. And then I can't find the NEMA stepper 23. Instead, I found a design of NEMA stepper 17. And then at the bottom part, we give the counterweight here. Yeah, and this is the desired the angle. And the first time we thought that the arm was meant to be 45 degrees to the to the left, but and then we found out that it's way much easier and makes it will make a less space for the motor right here. So if it's 45 degrees, the placement of the motor needs even a bigger space in the back of the wheelchair. So we make it just straight. Okay. Uh, uh, Maybe if Bu Lydia and Pak Dedi wanted to tinker with the design also, I can share the link so you guys could join inside.
I have a question.
Yep.
Um, the rope, will it be to the pulley? Will it be smooth, or is it slippery to the pulley, or is it connected to the pulley, or
It's
do you
supposed
plan to?
it's supposed to be attached to the pulley, and
Huh?
it's
Attach?
supposed to be attached and slippery to the pulley, but there are no design for rope here, so I just take a rod, and then so just for to imply it on the design.
No. What I mean is the top one. I understand it will be free running. That one.
Mm.
But the one at the bottom, the red one.
Yep.
What are you planning to have with the friction of the pulley and the rope? Are you going to have a maximum friction, or are you going to have minimal friction, or are you going to fix it, or?
I think between the pulley and the rope, we're still counting on with minimum friction.
Okay,
Yeah.
in that case, it won't work. If you have a minimum friction between the red pulley and the rope, then when you turn the motor on, it won't work, isn't it? Can have you check it? Do you think it can turn?
No.
Okay. So how are you going?
Maybe this is if we use NEMA motor, but we have another plan that you said,
Okay.
Bu Lydia. Maybe we consider to use linear motor, because I searched on Google, and then they have a lot uh, quite heavy, so it can pull up to 200 kilograms. I think for this one, if we use linear motor, I think we can it can work.
Do you have the design for it? For this one, so I found that if you use this one, do you know what my input is, Gary and Alga? You know why it can't work? It can't work if it's slippery.
Yeah. I got what you mean.
Okay. You can refine this, or you can go to the other. The other concept is okay. If you still want to use this in the future, you have to make sure that it works, yeah.
Okay.
Before you buy
Maybe
it.
if we okay.
Okay, so that's.
Can you show us the next one?
Agak belum di unmute.
Elga, I can't hear you.
Okay. Sorry. So this is for the sensor design, but I'm wondering, I don't know, still doubt whether we can create it or not, because we cannot enter the lab right now. So I don't think I can get my sensor from there.
Yeah, we can. You can, as I mentioned to you, Elga, multiple times. So we will collaborate with Andrew. Yes, I'm Andrew. So he can do the experimental part if necessary. Okay. So yes, we
So
can.
for this also the sensor design.
Yes, yes. You have to teach him what to do. Okay. So he will do it in the lab.
Okay. And then for the sleeve design, and the same as the previous one, and this is how to place the sleeve on the arm. And then here's the pulley torque. The maximum force is 36. Maybe it's easier if I show you the calculation that I already done.
Mhm.
So for this one, we made a change for the height from the shoulder to the pulley. So before it's 10, now it's 12. And then here's the but a free body diagram. So there are weight here. This is the elbow, and this is the shoulder and the pulley. So there is a tilt, it's not horizontally linear, the pulley to the shoulder. Instead, it has a tilted directions. And then here to here it's 20 centimeter, and here the length is 12.
Okay.
So the 12 is here, actually here until here. So like this one here, from pulley to the shoulder. And then here I got the degree, it's 31. And then I apply moment at the shoulder. So it's only the force that affect this calculation. It's only weight, and also F sin 31 degrees, and we calculated, and then we got FP. So FP here, the
So you
force.
should draw it then.
Okay, so the force.
Okay. So the diagonal. Yeah. Okay. Yeah. Yeah. Fine.
Maybe Edgar, if I may suggest, you can recalculate using three-dimensional moment concept, yeah? Because the children has, as Ibu Lydia instructed 2 weeks ago, has some angle, yeah? Not completely straight or not completely to the side, but with an angle about 45 degrees or something like that.
But yeah, because of the design, for the simplest design, we make it 90 degree, Pak. We cancel the idea for the design 45 degree, like Gary already mentioned.
So the one that you mentioned in the beginning, that you change the angle to move it forward. In that case, you are not doing abduction, adduction. You are doing flexion, yeah.
Oh.
Yeah.
Is it?
Yes, different muscle then.
Okay. So is it allowed or not? So if it is not allowed, we have to go to the previous design, and then the design is maybe different from now.
Yeah, I think go according to the original design, which is for abduction and adduction, not flexion and extension. Abduction and adduction, but with a little bit angle, 45 degrees, according to what Ibu Lydia has instructed, yeah, 2 weeks ago. But still, it is the upper arm that is being activated, yeah, being withheld, not and going towards like this, but with a little bit of angle. Okay, 45-degree angle or 30-degree angle, something like this. Not extending, not extension like this, but this part, but not completely to the side, but rather to a little bit front. So this is the design of the pulley, yeah, to put it a little bit with an angle. So perhaps, yeah, you can use two-dimensional analysis, but you have to shift that. Otherwise, the three-dimensional moment calculation would also do.
If you still want to go forward, then you have to change maybe the sensor again, because it can activate from the different sets of muscle, isn't it?
Indeed, yes. So this design, your current design is for abduction and adduction, right? To move the upper arm, like to the side, the one that Andrew designed last year, not for flexion extension.
Okay. So we should do three-dimension calculation, but I think because we also have only 1 degree of freedom, so it's still a two-dimension.
Yes, of course, it can be done in two-dimensional analysis, but of course, you put in mind in your drawing, in your design, that the axis, sorry, the plane is not.
Yeah, yeah.
What is this plane? Frontal or sagittal? I forgot.
Yeah.
Not this
Yeah,
flat again, but with rotated
oblique.
oblique, yeah, with oblique rotated plane.
It's just the plane. It's okay. I mean, you can use two-dimensional.
Okay.
Just make
And
sure
then
that your frame of reference of the plane is diagonal.
it's different. Yeah. Then here the perimeter of the child arm is 17.5, and then so if I just assume it as a round shape or a cycle shape, so it come up with diameter arm is 5.6, and then so for this one, from the shoulder, this one to this one, this is 5.6, and then from here to here, it's 10 centimeter. So it becomes 15.6 centimeter. So if I convert to a meter, it's 0.156. And then here, because this is the free body diagram, this is the arm. So this is the skin, yeah, the outermost arm here, and this is the rope, like this, this is the B actually. Here the distance between red line and the blue line here, the thick ones. Here's the B, and because it's almost it should be as a degree, but for the calculation for the easier, so I assume it as 0, and then this is the calculation. So I put moment at pulley here. So there is there are three forces applied here. W and F sin 0 and F cos 0. And I got F, it's 19.62. And then here the illustration for the roughly illustration for the pulley system. So the counterweight and the F here, and here oh, this is the counterweight 4.9 if we use 500 gram, and if we use 1 kilogram, it's becomes 9.81. And then if I use 1,500, it will have for 14. And then here we assume that pulley has 5 centimeter radius and 2 system, and so the torque minimum 0.3 for the counterweight 500 and 0.8 for the maximum. And then for the 1 kilogram, for the torque minimum 0.2, and then the torque maximum is 0.7. And for the counterweight 1.5 kilograms, we have torque minimum 0.1, and then torque maximum 0.5. So, but I think if we use a linear motor, we don't need use counterweight, right, Bu? Because if I saw on the Google, on the internet and YouTube, it should be there is no counterweight. So
Yes.
just
But can you go back to the first? I can understand your maximum calculation. It's quite right, but this one, yeah, stop.
Yeah.
I don't understand you have a line that's curvy like that for FP.
okay.
How can a curvy line can pull something out?
Yeah. It's actually maybe what I tried to show here is that if we like here, can you see, like if we this pulley, and then we are at the initial condition. So I think if we just have 12 centimeter, the rope will attach to the
Yeah, if you are like this, yeah, your rope cannot pull that arm, yeah, because the
yeah.
the force there, yeah, so use your force here. Wait a moment, where is it? Okay, go down, go up, yes. So the force here, okay, right. So the force that pull is more from the perpendicular force towards the arms. So which is then F sin theta. Okay, so if theta is approaching to 0, theta is very small, or theta is approaching 0, sine 0 will be
Sine 0 0.
yeah. So it has to. That's why, like this. Can you show again the three-dimensional design? I will draw something. The Tinkercad design. I will annotate it there, so maybe it will be easier. Who has that Tinkercad design? Gary?
Yeah.
Gary, can you please share? Okay, can you please show the front? of the children, of the child. Puter, rotate it. Yes. Okay. Yeah. So perhaps it would be wise, yeah, if you have turn a little bit, rotate about the z-axis. Rotate about the z-axis. No, 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 no. That is y-axis.
Lateral view.
This is this one, yeah. Z-axis is
from side.
Rotate again. No, 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 no. That is y-axis. Rotate again.
From the side. Can show us?
From the side. From the side.
Yeah.
Yeah. So we can look the yes, but too much from the side. A little bit. Yeah. Okay. No problem. So what I mean is maybe it would be wise if the structure is you have the pulley here hanging, something like this. And this is, I'm not sure, then something like that. What do you think? So then the force that is used to pull, so since then F sin theta, right? Theta is approaching to 90 degree. So you will need the pulling force upward will be maximum. So you will need only minimum torque to pull that arm. Rather, if you are using like this now with very sharp angle, almost close to the upper arm, this is the theta, right? Sin theta is this very small. Okay, you will need a lot of torque to be able to pull this whole arm. Did you get it?
So you mean by to move the pulley upwards?
Yeah, to move the hand directly upward. So it is a hanging structure.
Just here.
Yeah.
Can you open my the one that I sent to you?
But is it okay, Pak? Because
Can you open it first?
Okay, it is in the one of the picture that Ibu Lydia has ever sent to you. To me, then I forwarded to you. Also in the Google Classroom, it is. I put it there, uploaded there. One of the available design, existing design in the market or whatever. Although it is not popular, but yeah. It is simple. It is not that difficult. Calculation also simple.
Can you open your email that I sent? I think I sent you last time. Elga, can you open the one that I sent you?
The block design?
No, the one that I sent with the linear. But I just want to highlight the placement of the pulley.
Wait.
The title is simplification. Okay. Can you? Okay, I found it now.
This one?
Can you see the difference?
Yeah, this right hand.
So there is a structure upwards.
Yeah.
Nearer to the elbow.
Here?
Yeah, and you see, that's
Uh,
what we are trying to illustrate to you. The one that also
Okay.
Pak Dedi said.
I'm sorry, I missed this one.
Okay.
I thought you.
It doesn't matter if it's linear actuator or anything, but the placement of the pulley is
Of the pulley, yeah.
forward. You understand why now?
Because it's easier to have to bring the arm up.
Yes.
Because
Yes.
yeah, because what we are considered last, me and Gary, we are just put everything back of the child, because if something happened, just or a bad something happen, so it doesn't pull to the directly to the child. So
Look, ideally, everything is concealed. It doesn't appear from front, but it will need a very good mechanical design, very strong mechanical design. This is our first design. What we want is functional, not yet from aesthetical point of view. I think from the simplest design will be the right part, yeah? Where there is a pulley right above the elbow. So because then the required force will be minimum, so you don't need very strong motor. Yes, it will not look nice because there is a hanging structure.
I think we did try to propose that one, that we said that we're gonna put the uh, pulley up,
The
but
pulley is
then
okay, but the motor is not. The first one you put a lot of motor and everything about here. You can put the motor down,
Yeah,
and the structure is only for the pulley.
yeah. So the
okay,
structure, the
because
hanging
we,
structure will not be very heavy. It will be quite light because it only need to have that pulley and rope. No motor. The motor will be still on the back of the wheelchair of the children. Okay, understand?
Don't put a lot of mechanism here, you like a motor and everything here. No, you just need to put a pulley here, and then a rod or structure as I draw there to hold it in place. Yeah. And the one that pulls the rope down can be linear actuator, can also be motor with a pulley. And if you want to, you can also use the NEMA 17 and convert it into linear actuator by using some screw.
and if we put the pulley at the above the elbow, uh, which part of the wheelchair or which part of the mechanism that we need to itu si pulley-nya kita attach ke mana? Where do we need to attach the pulley?
You can attach it to the back of the wheelchair.
So it will be
can,
like a hanger like that?
Yes. Like a bent, what you call it, pole for the flag, but it's bent a little bit.
Yeah.
You can do something like this. See. Oops.
Yeah, something like that.
Like that, yeah. And this is can be bent so that you make it simpler. You can just bend. If you have the design for this and you don't know how to manufacture it, you can send it to me. We can make it here, some of the part. The easiest one, you can also use the elbows for the PVC pipes. Do you know? And then you can combine it with the aluminum pipe on the same diameter. So the PVC pipes are very useful actually to make some mock-ups for things that is not that heavy. Did you get this picture, Elga? A few days ago, I
Yes,
sent it.
yes, but I missed this one.
Okay, it's
because
fine.
it's like, yeah, I'm sorry, I'm so sorry.
It's okay, it's okay. But at least you know what I mean, and you understand why the first one doesn't work, yeah, and then the second one also, and then now you can choose about the mechanism to pull it. Are you going to use a stepper or linear actuator? If you are using, you can also use the stepper as a linear actuator by putting a screw driver and the screw nut in it. It's very common in what you call it, 3D printer. 3D printer. If you want to see it clearly, you can open any advertisement on 3D printer on how to convert the stepper motor into linear. Hello?
Okay, Gary Elga.
Yeah, yeah.
So please revise the design according.
Can I want to ask a little bit about the design. Can you? I want to share screen.
You close your share screen, Elga, so that Gary can
Okay.
share a screen.
So it's kind of like that, yes?
Yes, that's right. But you can put the what you call it, this is too white, yeah.
Yeah.
You can put it on the back.
Which?
This thing can be put on the back.
So it's
yeah, this thing.
so attached
Yes,
back
yes,
like that.
yes.
That's here on the back. Yes.
Yes.
How about the?
Can we draw on it as well?
Yeah.
How?
Wait. Let me share the link first.
Yes. Can you put it in the chat?
Yeah.
Okay. I think it's take too long because I haven't opened it at all. I have to make a new account. That's all right. Just carry on.
It takes some time because that software.
So
just continue without it.
okay.
Just continue. It's okay. As long as you put the pole at the back of the, if this is the what you call it, the back of the chair, you can put it here, isn't it? Don't put it like that here.
Oh yeah, so it's more on the back kayak
Like that.
ini infus berarti Bu.
Yes.
Okay, Gary. So revise that design and maybe you need to recalculate again. Hopefully then the required torque will be less than the current one, which has an angle rope. So if it is from vertically like this, that it will pull immediately. The whole force will be used to pull the arm. Okay, and that mechanical parts can be, if as soon as you finalize, can be sent to Ibu Lydia for fabrication, manufacturing at Ibu Lydia's workshop. The sensors parts can be made by Andrew. Okay, and you order the the microcontroller and the motor. Possibly it can be done by Andrew as well, or otherwise can be sent to you for programming at your home, for example, and then sent to Andrew for assembly at the lab. Okay, if really necessary, maybe we can ask special permission to use the lab just at one day. Yeah, not long. So if it is not finalized yet, so the parts can be done at separate places. Yeah, then maybe the final assembly can be done in the lab. That's just the idea. Okay. Any questions?
Any question?
Yeah.
Are our discussion clear for you all?
Not very clear because
Which one?
of saya tapi belum bisa ngaplikasiinnya soalnya kayak mesti ditaruh di desainnya dulu, ntar kayak saya baru ada pertanyaan lanjutan gitu.
Okay, nggak apa-apa. Just contact me via email. The first one I respond, and then second one I respond. It's just the last one I don't have a time to open it. Sorry.
Yeah, that's fine, Bu. Nggak apa-apa.
Okay.
Kita
So,
tahu Ibu sibuk.
Make it quick, yeah, Elga. So today is already week 12. So if possible, analyze all the design by the end of this week or at the latest by next week. So then
Yes.
Andrew can already develop the sensor also using the clothes, etc. So what material you need, tell him to purchase. Yeah, it will be covered from maybe my research grant. Then the manufacturing of the mechanical parts, the hanging part, the pulley can be done at Ibu Lydia's workshop. And then you yourself can order later the motor, yeah, as well as program the Arduino. Maybe then also need some Arduino programming. Yeah. And the interfacing of the sensor also need to be thought as well. How to interface all this, how many sensor you use, and all the design.
So have you decided which actuator are you using in the end?
I think it's better if we use linear because it's like 98% it's works. Tapi itu harganya emang juga mahal sih.
How much?
Like 700 rupiah.
700,000.
700,000.
700,000. How many you need?
This one.
Just one. Okay, it's still affordable. Yeah.
Soalnya saya ngelihat kan itu masih itu dia bisa. Tapi kan dia ini ya Bu, apa yang saya ada cari-cari, ada dia yang murah. Saya nemu, boleh saya share screen untuk yang terakhir kali Bu?
Silakan. Yes.
Bentar. Saya nemu yang ini Bu, apa namanya?
In English, try.
Oh yeah, okay, sorry. And I found this one. Okay, I think this is the used one. It's not new, I think, but the price it's much cheaper. But here they say that just jangkauan is just 10 centimeter. Is it just like how they can move, right? This 10 centimeter. Is it means by jangkauan kita?
Yes, 10 centimeter is the extension
Yeah, extension.
range. The range.
Yes, the
Range.
range.
From the minimum to the maximum extension, yeah.
Yeah.
That's why I asked yesterday, how much do you need?
Yeah.
If it's still on your range, then it can be used. But be careful with the used one. Sometimes I got the one
Wow.
that doesn't work at all, and then
Oh,
it's just
Yeah. Better to
difficult to
purchase new one.
complain.
okay. This is the new one.
Difficult.
It's just 700. Yeah, more than 700,000 rupiah. This is,
But the
but
stroke length it's the same, yeah.
yeah, but they didn't say. They don't say how much the range can the linear can be moved.
Yeah, that's stroke length. There is a stroke
Is there a
length.
stroke
there.
length is
Oh
what
yes, stroke
millimeter.
length. The same.
So it's the
10.
same.
What you can do if you want to have longer extension is you can have a gear mechanism to amplify the stroke length into the final extension of the rope at the pulley. Okay.
But you can also choose. You can also choose the one that's according to your necessity, because it comes with different stroke length. I think you haven't read that it has a stroke length.
Yep.
Yeah. So that's why you need to specify in advance how how long should it will move. What's the required range? If it says it's 15 millimeter, 15 centimeters, then find the one that has 15 centimeters. But if it's only 9 centimeters, then this one can be used.
Yeah. Okay.
Okay. Fine.
Yeah.
Okay.
Okay. That's final.
Finalize your design, please, and I will put the assignment in the Google Classroom for you to upload the current presentation as well as calculation and the design, and then finalize this week or maximum until next week. And the material for the components for the mechanical assembly can be fabricated in Ibu Lydia's workshop. Sensor can be done in our lab. Electronics can be done in our lab. Yeah, and you ask Gary's help. Programming, you can make the program first and ask, not Gary, sorry, Andrew. Yeah, Andrew to upload. If really necessary at the final stage, maybe just we will ask special permission one day, maybe after the final exam or something like that.
If you want to simulate what you have learned so far, you can probably put it in a, do you have any chair at all? And then the back of the chair can, not necessarily a wheelchair, but just any chair that is sturdy enough so that you can put the mechanism later on that back. I will put the mechanism on a piece of wood, but you still need to put the wood into a chair so that somebody can sit on it.
We can try the chair in the lab, yeah, laboratory chair for that purpose.
Okay. Yeah, I think that's all.
They seem to have non-convincing eyes yet.
Yes. Okay, tell us again what you need, and probably if there is something that is not clear.
Yeah, nanti. So Anna, I will tinker with the design first, then I'll have some questions.
Maybe for the real design, it will be much more questions.
That's fine. You can contact me after this as well, but yeah, not 3 times in a week.
Yeah.
Okay.
Okay, thank you very much. Ibu Lydia for coming, and hopefully Gary and Elga can finish the design soon and then start to
Yes.
fabricate and manufacture. Because yeah, I think it's the program also the program itself may not be that easy. Yeah, so be careful. So
Yes.
you need to program according to the sensor and then the correct stepping, the step size, etc. Yeah, so please do not also finish this mechanical design soon, and then so you can get also tackle the other electronics and programming problems. Okay, with that, I would like to conclude this session. Thank you very much again to all, and have a nice afternoon. Bye bye.
Thank you, Pak. Thank
Bye-bye.
you.
Thank you.
Thank you.